Want accurate color measurement in oils and fats? Don't just rely on technology, master the technique. Welcome to this technical know-how session presented by Tintometer India. In this video, we'll take you through the essential do's and don'ts of using the Lovibond RYBN color scale on the visual Tintometer Model F, trusted worldwide for edible oil color measurement. Getting color analysis right isn't just science, it's trust, quality, and compliance. The Lovibond RYBN scale helps you maintain consistent product appearance, identify contamination, and meet industry standards like AOCS, ISO, and BIS. Precision depends on a process, and this session is all about mastering that process. In the next few minutes, you'll learn how to prepare your samples correctly, what to avoid when handling the instrument, the importance of using neutral glasses, importance of proper lighting, and how to make accurate visual matches that aligns better with global standards. The image over here is of the Model F optics, where you can clearly see the halon block, the diffuse glasses, and the glass racks, along with the eyepiece. This is the Lovibond RYBN gamut, which covers the entire visible region of the electromagnetic spectrum. The Model F red, yellow, blue, and neutral rack covers the visible region. Mostly the edible oil falls in the yellow to the red color region of the gamut. The individual RYBN in the rack covers the following range. The red has 3 racks. The yellow has 3 racks. The blue also has 3 racks and are 2 neutral racks available. The red goes from 0.1 to 0.9. The second one goes from 1 to 9. And the third rack goes from 10 to 70. Likewise, for the yellow, the blue, the first rack goes from 0.1 to 0.9. The second from 1 to 9. And the third from 10 to 40. Neutral, the first rack goes from 0.1 to 0.9 and the second 1 to 3. Let us now look at the most important do's and don'ts for using the RYBN scale accurately. Follow these steps to get trusted, consistent results every single time. The first step is the selection of the operators. The color vision needs to be tested and retested every 5 years. No tinted or light-sensitive glasses are preferred to be worn at the time of analysis. This is a visual color match. We at least recommend to have 2 to 3 operators and a consensus to be reached. At least 2 operators, if are agreeing to a single result, that particular result can be acceptable. If all 3 are having different results, maybe a 4th operator could come in. But it is important that all these readings are taken independent of each other. The international standards also recommends that the eyes should be rested for at least a 30-second gap before matching for the second sample. The test must be carried out by at least 2 trained operators. The second most important point to remember is the preparation of the test sample. It is essential that the oil is completely liquid, clear, and bright and free from any kind of turbidity. Cloudiness or semi-solid samples are not recommended as they may distort color perception. If the test sample is not liquid at room temperature, heating is recommended 10 degrees above the melting point. Now you may just ask, how do you reconfirm a clear sample? For that, it's a very simple test that you can do. You could place any text behind the cell, and if you're able to read the text, the sample is perfect for analysis. And if not, the sample is not fit for the analysis. The third aspect to remember is heating the samples. A lot of times, samples are heated in a water bath or in an oven and then got to the system for analysis. Heating causes the hot oil to rise and leads to convection current formation. Something that you can see over here. The best way to tackle these kind of sample convection currents is to just use a simple glass rod that you can see here and stir the samples well. That will take care of any kind of sample convection currents. Thing to remember and to note down is temperature. Every oil is affected differently by the temperature. So the following 4 slides will show you how. In this experiment, what we have done is we have taken the temperature on the x-axis and the Lovibond respective units on the y-axis. On this image, we have plotted the Lovibond blue units against temperature. We have taken different palm oils from palm 1 to palm 7 and subjected to these temperatures. For example, if we pick up palm 1, at 40 degrees, the value of the blue units is somewhere around 3.3, which subsides to almost zero at the temperature of 50 degrees, which is a clear indication why temperature may impact the values that you are observing. Blue is also an indicator of turbidity, so it is recommended that the sample should not have blue unless and until the nature of the oil is completely bluish or greenish in color. Attribute can be seen when the red units are plotted against the temperature. If we again pick up palm 1, the value at 40 degrees is somewhere around 4.3 and subsides to almost 3.4 at 50 degrees and then gets stable. If you look at different palm oils, each of them are showing different values at different temperatures. So the effect of temperature is not consistent across all palm oils. However, noting them down is very important in order to ensure that the side-to-side color variations for the similar sample is not obtained. The yellow, when plotted against the temperature, also has a similar observation. For the same palm oil 1, at 40 degrees, the value of the yellow is 27, which comes down to almost 23 at 50 degrees Celsius. The next slide will show the impact of temperature on the neutrals. Here, palm 1 can be looked at 40 degrees, the value is somewhere less than 0.05. At 50, it goes to almost 0.3 neutrals and again comes down at 60 degree to less than 0.15. So important point to remember is to note down the temperatures across the different sample analysis. The other aspect, which is very important, is the path length. Here, if you look at this image, different path lengths are taken, but for the same sample. At a shorter path length, the oil appears lighter, and at a longer path length, the oil appears darker. Reason being, at 1 mm or a shorter path length, you load less amount of sample volume, so the color looks less saturated. However, when the same sample is taken in a longer path length cell, once you are loading more amount of sample volume, so automatically the color looks more saturated and darker. So for lighter oils, we recommend using a longer path length, and for darker oils, we recommend using a shorter path length. We have also launched the 1 mm shortest path length. How it works is by taking a 10 mm path length cell and using a 9 mm glass blocker. The sample volume is loaded to a very low height and then the glass blocker is inserted. The oil rises because of the capillary and one can use these shorter path length cells for very darker oils like mustard oil. So whenever the Lovibond sum of the units red, yellow, blue and neutral exceeds 20, the path length should be reduced. Let us now understand the Lovibond RYBN scale a little more. The logo that we have also reflects the Lovibond RYBN scale. Now, the Lovibond RYBN scale is not a linear scale. What I mean, it's not like the rulers that we have studied in our school days, where every value is equidistant from each other. So 0 to 10 will be same, 20 to 30 will be same, 50 to 60 would be same, so on and so forth. What we have as Lovibond scale is a logarithmic scale. Reason being that it tries to cover the entire visible region of the electromagnetic spectrum. Covering that region using a linear scale is next to impossible. So a logarithmic scale is much more convenient to measure these longer distances in shorter steps. What we mean by a logarithmic nature is the values or the distance between two units are not the same, unlike a linear scale. The distance, which is basically implying the color difference, is more between 0 to 10, Lovibond units. As and when we keep on increasing the values in the Lovibond units, the distance or the color difference keeps on decreasing. So a value of 30 to 40, the distance as well as the color difference would be far more less as compared to the distance or the color difference between 0 to 10. In the RYBN scale, the yellows are the most impacted because of this logarithmic nature. This image on the right will elucidate that further. Let me zoom it and then you'll be more clear. Looking at this image over here, 0 to 10 is covering a huge amount of distance, 10 to 20 covers a far lesser distance, and the distance keeps on decreasing till the time we reach 70. So technically 50, 60, 70 are very, very close to each other. This distance, as I said, is implying the difference in color. So two operators, if one operator gets a value of 3 and the other operator gets a value of 5, numerically it may look like a very low difference, just 2 units. But actually, because of the logarithmic nature of the scale, the color difference is huge enough. However, if two operators on the model F get a 30 Lovibond yellow unit and a 40 Lovibond yellow unit, it may look like a 10 numerical difference, but the color difference is very, very less and hardly noticeable. The next time when you're measuring the Lovibond RYBN color scale on the Model E or the Model F manual system, remember that the scale is logarithmic and two operators who may have different values of yellow as 30 and 40 are both correct because technically the color difference is very, very negligible and one should not look at the numerical difference. And as a guide, which was also mentioned in my previous slides, whenever the sum of the red, yellow, blue or neutral exceeds 20, the path length can be reduced so that the volume of sample loaded is lesser, the color appears lighter and in the range so that the color difference becomes noticeable. Another important aspect of the Lovibond scale is neutrals. A lot of people do not use them or maybe do not know why we use them. It is important to adjust brightness with the neutral wax when measuring the Lovibond color. Let us take an example. Over here, light is coming from the lamp with 100% intensity. And then we try to match the color with the red rack as 2 units, then the yellow as 6 units, and the yellow again as 0.4 with the eyepiece. Every time the light passes through a glass rack, there is a reduction in the light intensity, almost by 8%. So by the time the light reaches our eyepiece, because it passes 3 different racks, we have already lost a 22% of the overall light. In order to compensate for the lost light, neutrals are much more recommended. Remember, not all oil samples have to meet the requirement of neutrals, but using them would ensure that you're unnecessarily not increasing the reds and the yellows. The image below are perfect example of having a match without using neutrals, which is here, and having a match when the neutrals are used. So when you have a neutral value, you know the match is perfect, unlike the one where you do not use the neutrals. Another point to remember is that the instrument service and maintenance is very important. We offer all our services from Tintometer India directly. A lot of customers complain of inaccurate readings and inconsistency in their readings. That could definitely or be one of the reasons of that could be that the instruments are not serviced properly. The halon block may have yellow spots. The sample chamber is not clean enough. The racks are not aligned well. Or maybe these individual glass racks have not been cleaned. Remember, we are working with oils. And as we see when we work in our kitchens, because of the usage of oil, the glasses gets very, very sticky. Similarly, these Model F racks also are made of glass pieces. And if they are not cleaned frequently or serviced properly, they may affect your readings. One has to be trained enough to clean them and put them back. If any kind of alignment issue comes in each of them or one of them, the results will completely get disrupted. So, maintenance matters. Keep your instrument in peak condition. Always check, is it clean, unmodified? Do you know its service history? Are the sample cells scratch-free? Remember, great data starts with great care. A final checklist. What you need to ask you and your team. Is the Model F unmodified? A lot of people, they modify the bulbs, the internals, they paint it, they put a piece of paper on top of the halon lock. These are just a big no-no. Are the instruments clean and undamaged? Are the cells clean and undamaged? The cells have to be cleaned properly and always maintained. A lot of people buy local consuming cells. These cells may have glass alignment issues and may disrupt your results without you noticing them. So always go for the cells which have the brand of the Lovibond on them. Is the service history of the instruments known? Is the Model F data from more than one user, or you're only relying on a single operator? Have the Model F users been recently eye tested? How is the Model F being used? Are you using the Lovibond RYBN scale or the RY or anything else? Are the samples to be measured transparent? Temperature is being recorded? Are the samples filtered and checked for turbidity? If samples are heated, are you heating at the temperature 10 degrees above the melting point? If heated, are you being stirred constantly or regularly? Is the path of the cell path length appropriate for the Lovibond RYBN values and noted because of the same sample checked at two different sites at different path lengths would give different readings? Are you taking into account the known variation between observers? If not, you can again write or contact us at the shared email address or the mobile number. We will be happy to help you. So thank you so much for attending this technical know-how session. I hope it was helpful and would at least elevate how you think and how you work with the Visual Model E or the Model F and measure your edible oil color. The next time you have questions, please do not forget to write to us. Subscribe to our YouTube channel and you can leave your comments in case you want more such tutorial videos that will help you to do a better analysis using the Lovibond scale.